Our sun, the anchor of our solar system, is a celestial powerhouse. It bathes our planet in light and warmth, sustaining life as we know it. But the sun is not always a benevolent neighbor. It can unleash bursts of energy, reminding us of its awesome power. Recently, the National Oceanic and Atmospheric Administration, or NOAA, detected one such event, an X2 solar flare. This eruption on the sun's surface was captured by NOAA's advanced satellite technology, providing scientists with invaluable data about these powerful events. This image serves as a stark reminder of the sun's immense energy and its potential impact on our planet. The flare, classified as X2, represents a significant event on the scale of solar outbursts. To understand its implications, we must delve into the nature of solar flares and their classifications. Imagine a sudden flash of light on the sun's surface, a sudden release of energy equivalent to millions of hydrogen bombs exploding simultaneously. That, in essence, is a solar flare. These intense bursts of radiation are the most powerful explosions in our solar system. They are categorized based on their strength using a lettering system: A, B, C, M, and X. Each letter represents a tenfold increase in energy output, with A-class flares being the weakest and X-class flares being the most intense. Within each letter class, a finer scale from 1 to 9 further categorizes the flare's strength. An X2 flare, like the one recently observed, signifies an event twice as powerful as a standard X-class flare. These are serious events capable of causing noticeable disruptions on Earth, particularly to our technology-dependent world. The Earth is not directly engulfed in the flames of a solar flare, but the effects can be felt across the vastness of space. When a flare erupts, it releases a surge of radiation and charged particles that travel outward at incredible speeds. This solar wind, as it's known, can interact with Earth's magnetic field, causing geomagnetic storms. These storms, in turn, can disrupt a variety of technological systems we rely upon. Satellite communications, crucial for navigation, communication, and data transfer, can be significantly affected. Power grids, the arteries of our electrified world, are also vulnerable to these disturbances. In extreme cases, solar storms can induce currents within these grids, potentially leading to blackouts and widespread disruption. Understanding and mitigating these risks is a vital aspect of our technological resilience in the face of space weather. Guardians of the Sun, NOAA's vigilant watch on space weather. Fortunately, we are not unprepared for the sun's occasional outbursts. NOAA plays a crucial role in monitoring and predicting space weather events like solar flares. Using a network of ground-based observatories and sophisticated satellites, NOAA keeps a constant watch on the sun's activity. These observatories capture images and data across various wavelengths, providing a comprehensive view of the sun's behavior. The GOES-R series of satellites, for instance, are equipped with instruments that can detect solar flares, measure their intensity, and track the progress of coronal mass ejections, or CMEs, massive bursts of plasma and magnetic field that often accompany powerful flares. This information is crucial for issuing timely alerts and warnings, allowing us to prepare for potential impacts on our technological infrastructure. The solar cycle. Predicting the rhythm of our star's outbursts. The sun's activity, including the frequency of solar flares, is not constant. It waxes and wanes over an approximately 11-year period known as the solar cycle. At the peak of this cycle, known as solar maximum, the sun is at its most active, with more frequent and intense solar flares. Conversely, during solar minimum, the sun is relatively quiet. Understanding the solar cycle is crucial for predicting the likelihood of space weather events. By analyzing historical data and observing current solar activity, scientists can make informed predictions about the timing and intensity of future solar cycles. This predictive capability is essential for mitigating the risks associated with solar flares and other space weather phenomena. Cosmic hazards, solar flares, and the perils of space exploration. As we venture further into space, the hazards posed by solar flares become even more significant. Astronauts on missions beyond Earth's protective magnetic field are particularly vulnerable to the radiation bursts from these events. Exposure to high levels of radiation can have serious health consequences, increasing the risk of cancer and other radiation-related illnesses. Protecting astronauts from the dangers of space radiation is a paramount concern for space agencies worldwide. Spacecraft designed for deep space missions are often equipped with radiation shielding to protect their crews. Additionally, mission planners carefully consider space weather forecasts, adjusting mission timelines and activities to minimize the risk of exposure to solar storms. The importance of vigilance, continued monitoring, and the future of space weather prediction. The recent observation of an X2 solar flare serves as a potent reminder of the sun's power and the importance of continuous monitoring and research in the field of space weather. As our reliance on technology grows and our spacefaring ambitions expand, so too does our vulnerability to the sun's unpredictable nature. Investing in advanced monitoring systems, improving our understanding of solar physics, and developing more accurate predictive models are crucial steps in mitigating the risks associated with space weather. By unraveling the mysteries of our nearest star, we not only gain a deeper appreciation for its awesome power, but also empower ourselves to navigate the cosmic ocean safely and responsibly. The future of space exploration, and indeed our technological civilization, depends on it.